Hi all, this is Vasu Sham, and I'm joined today by Sean Seet. Hi, Sean.
Hello, yeah, it's great to be here. Thanks for inviting me.
Well, thank you for joining on short notice. So Sean is a PhD student here at Cambridge, working with David Skinner on twisters. So could you briefly describe the focus of what you specifically are interested in?
Right. So most recently we're interested in twisters on ADS5. Yeah, as a symmetry reduction of the twistor space of R6. I mean, the long-term goal is to compute correlators on it with some kind of world sheet model. So to reproduce the successes that were had in the early 2010s with the ambitwister string of Mason and Skinner on flat space. Yeah, we're hoping that we can do something similar on ADS5.
That's very cool. So this is going to be second in the series of Twister excursion episodes. And last time we just got up to understanding what twisters are on R4, well, R31, complexified Minkowski space, really. But now we're going to see what they're good for, starting with one of their first use cases, which was describing sort of zero rest mass classical fields of arbitrary spin. Basically, they're field equations in the self-dual and anti-self-dual sectors. And this is encapsulated in what's known as the Penrose transform. So that's the ambition for today, is to understand what the Penrose transform is. So I mean, how would you start by describing it? Because there is a fairly unambiguous mathematical statement, but what would you, how would you see this fact?
Right. So okay. So the statement of the Penrose transform is something relating d-bar closed objects on twistor space with the ZRM equations. Yeah. And the intuition behind this is that once you define your complex structure, once you define a complex structure on this on twistor space, you say there exists this d-bar operator that we're going to use. The thing about the d-bar operator that we use canonically is that one of the directions is up the P1 fibers, and two of the directions are sort of in the space time. And when you say that d bar of this object vanishes, what you're sort of saying is that included in that statement is some claim about flatness in the space time on some components of your H01. Yeah, and then that thing is the thing that eventually becomes the ZRM field.
Right. So we should just clarify, by ZRM you mean the
sorry,
zero rest mass fields.
Yeah.
But yeah, and I guess you're saying that there are these objects that are d bar closed but not exact in twistor space,
Yep.
Which basically correspond to such zero rest mass fields, self-dual and anti-self-dual pieces of these fields of arbitrary spin.
Yes, that's right. Yeah.
That's cool. So I guess we should lay out some notation before getting to meet this fact. So just a second, or you could use the tablet if you'd like. Lay out your own notation.
It's okay. I think I'll follow the notes. That's all right.
Yeah, no worries. Great. So here. Yeah, so what the zero rest mass okay,
it's okay.
in the frame.
Yeah.
So what these fields are basically fields that I can write in terms of only dotted or undotted spinor indices, right? So I have one of this kind. So let's call this clarify. I have yet another of this kind, which I put a tilde on, although it doesn't strictly matter. Yeah, let's not do that. these are two components of the same object, so I'll just keep this convention. And we have two sectors, and I think the convention is to take self-dual to mean that the undotted vanishes. So we're in the sector where and the equation of motion for the remaining field is dot theta alpha of this whole thing. No, it's the other way around. Dot. Let's just go 2 all the way dot s. I should mention that these are completely symmetric in their indices, in their dotted or undotted indices. And I think that the anti-self dual is just replace the dots with the undotted. And it's the same kind of condition.
Yeah, exactly.
So I mean, I guess it's a question of which we prefer to work with for the purpose of this discussion. What's the more convenient one? But let's just so here we have alpha so the role between these two objects is exchanged. So I'll just write that down. Okay, cool. So let me just zoom into this.
Right.
So the idea is that this condition will somehow become d bar closeness on twistor space. So we should just recapitulate that there is a complex structure on twistor space, and we can define now a Dolbeau complex associated with this, where we split the exterior differential between holomorphic and anti-holomorphic parts. And we use, presumably, the incidence relations to relate the space-time derivatives appearing here to some kind of d-bar operation on twistor space. So presumably we should start by just explaining what's going on. So what we're after now is what the Dolbeau operator is.
Right.
So abstractly, let me just start a new section. So do I want to spell this? No. Right. So first, like what the notes, which are Tim Adam's notes that we're still using, explains, is how you define a basis of vector fields and their dual one forms with respect to a given complex structure. But I'm wondering if there's a way to see this a little bit more clearly. So I do know that if I was to go and find this relation between a bitwistor X and so there's like some relation between sorry, it's because I don't know how to spell right. So yes, presumably from this I have enough information to take the space-time derivative and then associate it to whatever it is that should happen in twistor space. But I'll just write down the result, and well, we'll see what what happens here. So the idea is that we have the tangent space at some point z of, right, but we have basically the left half of the complexified tangent space. So we're going to take 0, 1.
Okay. Yeah.
Right, and this is spanned by well, presumably there should be like a mu dot alpha dot component and a lambda component.
Yeah, that's
but
right.
now
Yeah.
we've sort of hatted them
Yes,
because
yes.
it's the d bar component.
Yes.
Right?
Oh, yeah. So yeah, we are working Euclidean signature, right?
Yeah,
So
So I should
yeah,
just
so there's
mention.
two. Yeah. So yeah, that's the best way to think about it. Really. Yeah, it's just the two. So usually when you start off with PT, right, it's CP3, right? It's just and you have homogeneous coordinates mu lambda. And then
Right.
when we cut out infinity, right, we say that so we one CP1 corresponding point at infinity. And that's good in several ways, right? First way, it makes the space a bit more interesting because the cohomology on CP3 is just this is just completely useless to us. It's all 0 anyway. But once you've done that, then you have some interesting cohomology. And the other thing is also that once you've done that, it makes sense to pick a patch of coordinates in which lambda is non-vanishing. So
Okay.
you can write you can explicitly write coordinates where mu are coordinates on C2 and lambda homogeneous coordinates on CP1. And then once you've done that, this becomes much easier to write down because then the anti-holomorphic okay, I'm not used to thinking of the tangent vectors, so I'll have to describe the one forms first and then dualize. But okay, so the one forms would just be the two d mu hats and lambda hat d lambda hat.
Okay, so they're spanned by so the d hat mu.
Yep, the 0 and 1 part of those, and then and
well, yeah. So there's some
index on them.
Dot alpha.
Yep.
Yeah, because the hat doesn't do anything to the dot in Euclidean signature.
Yep.
And so this I'm calling E. So everything is barred. So this is E. Okay, I'm doing this in the wrong line. My audience is used to this by now. So yeah, for convenience, I call this that. And then there's another thing which is bar E naught, which should just be d hat lambda.
Yes. But people like to so the lambda hat d lambda hat is the component which doesn't point in the scaling direction. Since we want to throw away that. And then but people like to remove all the hatted weight by dividing out by lambda hat squared.
Very good.
It's not totally necessary. It does make calculations easier.
So you mean that people like doing the following. We take where did m come? Well, okay. So we take so let's write this a little bit more neatly. And then you could probably reiterate as to why this is done, because of the CP1 nature, or the P nature of CP1.
Yeah, exactly.
Right?
Yeah. So you want to throw away the thing that's dual to the thing that scales lambda. So that's the Euler vector field in the homogeneous coordinates, which is lambda contracted into d by d lambda. Okay. And the thing that's dual to that is unnecessary. Oh, sorry. I guess we're things to talk about hats. I should say the thing that's dual to lambda hat d by d lambda hat. It's totally unnecessary, so you throw it away. So so there's a hat on the so the lambda hat d lambda hat. It's the one that
lambda hat d lambda hat. Okay, sorry. Okay. Yeah.
So sorry, let me find it.
Right. So let's see if I understand what's going on here. So do I need to square this, or is it just going to be to the power 1?
Usually people like to square it so that it balances all the anti-holomorphic weight. So
Okay.
so they never have to count powers in lambda hat ever.
Mhm.
They only want to count numbers in powers of lambda. Yeah,
I
so
see.
they tend to prefer this.
I
Yeah.
see. I see. And so D mu hat presumably has also yet another relation to D, well, the thing that we want because of the
Yes.
incidence relations.
Yes, exactly. Yeah. So this basis can be rewritten with the derivative only acting on x, since the lambda hat derivative, you can just add some amount of the e bar naught to remove it.
Uh-huh.
So you can write it as a lambda hat dx over lambda hat. But
Okay, let's
yeah.
let's go through that. So just go through this a little slowly.
Oh, yes.
So we have hat mu
Where did he put this?
dot alpha equals x alpha everything hats.
Oh, you define it right at the start. Yeah. Okay, makes fair enough. Yeah.
Okay.
Yeah.
So we have the incidence relation, and I just take D through this,
Yep.
right? And so if I wanted bar E of dot alpha, then what I'm gonna have is dx alpha dot alpha at lambda alpha plus, wait, yeah. And
Yeah. So the way to see that this is actually the basis of this thing is actually the way to see that you can actually just have, so the basis spanned by these three is the same as the basis spanned by E bar naught and just that first guy, which is that you resolve the identity between the x and the d lambda hat with lambda hat skewed over the indices
yes.
over lambda hats, and then the lambda d lambda hat part, throw it away because it doesn't point, it points off into C4, right? It doesn't.
Oh yeah, so sorry. So actually, let's
yes.
break this down a little bit more slowly.
Oh, yes,
because you
sorry.
mentioned this. So
Yep.
the idea is that you have lambda parametrizing CP1.
Yes, that's right.
And then you have mu dot parametrizing
C2.
C2, right? Which is basically like complexification of R4.
Oh yes, sorry, yes.
So the idea is that we're really looking at the Euclidean signature. This twistor space is like a vibration of CP1 over
yes.
R4.
Yes.
And so you have naturally this kind of
yes.
Story where you have the CP1s parameterized by lambda, and then you have the mu, which is complex and has like the R4's worth of information, which is
I can write down how.
Sure, yeah. Go ahead. Yeah, you can you can share. Let me stop sharing. You can share.
Oh yes. So exactly. So the nice thing about working with in Euclidean signature when you have the hat conjugation is that the amount of information that, as you say, this C2 cross CP1 and the R4 cross CP1, we're going to see this explicitly, but the amount of information that you have in mu and lambda with the hatted operation, with the hat operation, it's exactly the same as the information you have in this set of coordinates, right? So it's you can see that so first thing is that from CP3, the twistor space CP3, the reason we can go down to this patch and not lose any information is because we throw away the lambda equals 0, right? And according to our incidence relations, it corresponds to one particular point that we're throwing away.
Yes.
So we're throwing away point at infinity to go from S4 to R4. Okay, so there's that. And then the way this works is that X is actually totally you can decompose X into its into 4 components, right? And the 4 components are simply mu hat X lambda hat, mu hat x lambda, mu x lambda hat, and mu x lambda.
Yes.
Yeah. So yeah. So these two actually just carry the same information because
Okay.
of because with the under Euclidean hat conjugation, lambda hat is non-zero, and mu hat is non-zero. So these since this lambda, the index is two valued and mu index is two valued, these form a basis of each form a basis of the like lambda hat form a basis of the space of dotted spinors.
Yes.
Mu hat from the of dotted spinors. Sorry, undotted spinors.
Undotted, yeah, this is dotted, yeah.
Yeah.
No, very cool, very cool. Yeah, and so continuing on what we were doing, basically what you said was that if we took the x
oh yes, of course,
differential, then
yeah. So we have dx lambda hat.
Yeah.
So lambda hat dx plus xd lambda hat, and then the claim that I was making earlier is that this basis, right, lambda hat squared d mu hat, the span of this, right, which is it's going to be the 0,1 forms on the twistor space for Euclidean R4.
Right.
This the span of this is the same as the span of this lambda hat d lambda hat over lambda hat squared lambda hat dx over lambda hat. Right, and
yeah. So we're off by just this second thing that appeared in the yeah.
So of course this thing. So if I'm not lazy about the indices, the way it actually looks is this lambda alpha lambda hat beta desymmetrized over lambda hat up to some number, which I'm still being lazy about. But
sure.
Yeah. So the point is that the lambda d lambda contraction, lambda d lambda hat contraction actually points off of the quadric, right? The way you can see that is that it's not killed by the dilatation of the lambda hat. So this part is something to just throw away. So the remaining part is the part where you have x lambda.
Yes.
And then the lambda hat d lambda hat.
Yeah.
Yeah, and then of course the span of this thing is in the span of the first term. So
right. So basically, in some sense, this is there's this redundant piece, which basically falls into the first basis element, as it's just along the first basis element. So and then there's the mysterious number, but that number is just the thing that
it's just a number.
That's very cool. So now we have so what you're saying is that we should really think of this. Yeah, exactly. So we think of d mu hat as lambda hat dx over lambda hat, which is a useful relation because the dual vector field statement of this will allow us to translate partial. Or it doesn't really matter. I mean, we know now how to take the exterior differential, or the half the Dolbeau differential, which is d bar now is going to be given by E naught. Well, I guess
sorry,
I'm more explicitly. No, that's perfect. Lambda partial lambda hat, yes.
Plus, this part is a little bit annoying to get right, but do my best.
Nice, very cool. So this is basically the thing whose action on something being zero shall be equivalent to the zero rest mass field equations.
Yeah, exactly. So it makes a statement about this acting on a component of the not common one form that we're gonna act on.
Yeah, actually, so let's just write that statement down, right? So there's like gonna be, so let's just write down the closeness under this operation, and let's try to recover that equation we had before.
Yeah. Okay. So, wait, sorry. Is it that part yet? Or,
yeah, I mean, like we could go the other way. The notes does it in one way. We could go the other way.
Right. Yeah. Okay. Yes. So yeah. Okay, to do this part, we'll be starting with Woodhouse representatives. Is that okay?
Okay, yeah, please tell us what that is.
Oh, okay, yeah, okay. So
So yeah, just to mention the correspondence between solutions to the so just to remind everyone, the correspondence between solutions to these zero rest mass field equations and these d-bar closed forms, but not d-bar closed but not exact forms on Pfister space is the Penrose transformation.
Yep.
Yes.
This equals to S.
Yes.
S minus 2. Sorry, minus 2S minus 2. This is the negative homogeneity one. Yeah.
Right. So we should just explain that in addition to saying that these are forms annihilated by d-bar but not being closed, they also have a homogeneity degree that's in correspondence with the spin.
Yes,
right, with the spin of the field.
Exactly right. Yeah. Oh, sorry, I'm unable to scroll anymore. I don't know what happened here.
Do you wanna?
Oh, sorry. I might have to stop sharing it.
It's all good. It's all good.
Oh, the screen is frozen. Sorry, it doesn't normally do. Oh yeah. Okay, great.
We're back. Okay, so from here, so what are the Woodhouse representatives?
Okay, yes. So the Penrose transform is a way of realizing it this way for C4.
Yes.
A variety of signatures. The Woodhouse representatives. So give. Oh, sorry. Whoops. Sorry. Sorry.
This way.
Yeah, this way. Yeah. Yes. Woodhouse representatives are the other way. But once you've chosen the Euclidean reality structure and you're on R4.
Mm-hmm.
So given a space-time field that satisfies this, you can construct a H01 that
okay.
Yeah. And there's so his statements okay, so there's so in order to do okay, I'll have to talk about integration on CP1 first in order to motivate some of the steps.
Sure.
Okay.
Please go ahead.
All right. So when you integrate on CP1, right? So we're gonna work with homogeneous coordinates on CP1 all the time. That's the most convenient. We integrate something not one form on CP1. The first thing that you have to keep track of is that the weights have to balance. So all the weights, the total weight of in lambda has to be 0, and the total weight in lambda has to be 0. Total weight in lambda hat has to be 0 as well. Because otherwise, you're not doing something that makes sense. Because
you need a form to integrate over a cycle, and then
so that's okay, so that's one thing. And the other thing is a property that they call Naire's lemma, which is this. So you have this lambda hat, d lambda hat. The statement about pairing up of lambdas and lambda hats. So I suppose I have some lambda alpha 1, lambda alpha n, and then some that doesn't depend on lambda, maybe, and then you have some other lambda hat beta 1, lambda hat beta n phi tilde beta n x. Naire's lemma says that that if the weights balance, so that this is a valid integral to write down, right? All of these just pair up with all of these.
Okay.
Yeah, so you get some number, and then you get alpha fully contracted into alpha tilde.
Okay.
So so you get, if I write it in a less lazy way, you just get a bunch of deltas. Alpha, beta, and then phi alpha 1, and phi 2, beta 1, beta n. So this evaluation is a step that we will need.
I see. No, this is very interesting. It has a little bit of the character of
wait, sorry, I gotta put some
there's some other
weights in there. Yeah.
Okay. Yeah. So that's lambda hat. Not the x, just great. So what's interesting about this is that it has a little bit of this a little bit of the feel of these two things being almost like Fourier duals, but not exactly.
Yeah, precisely. No, you're exactly right. It's an excellent observation. So it comes from this little trick, right? That if I do this many times, so each of these has a as an index on them.
Mm-hmm.
Of course, this thing is equal to lambda hat alpha 1 lambda hat alpha n with some number, which, you know, I can be not lazy and write the number down. So it's going to be, you know, -1 to the n minus 1, then n minus 1 factorial, something like that. Oh,
Okay.
Yeah, but I'm going to be lazy about it. Sorry. So it's this really. So you can replace all of this stuff with
these
this,
derivatives with
and then
respect to lambda.
and then act the other way with them.
Right.
Yeah.
Okay, I see. No, that's very fascinating. So the fact, okay, so this is just some quirk of having to integrate over these homogeneous coordinates in CP1 that you don't, like, the kernel of the transformation, the analog of the Fourier transformation can just be written in terms of polynomials, because you have this rational, it's a rational function because you have this weight in the denominator. So I mean, if you try to define yet another variable, you can imagine that there's going to be some exponentials. Like, you know, if there was a logarithm of something.
So again, you're right. It's you can do the Schwinger parametrization of this. Could
we see that? That would be very fun.
I have to specify a contour, I suppose, but okay, I'm gonna be a bit lazy about it. Just some contour. T over T. And then, of course, this thing is up to some number. I'm gonna be a bit sloppy. You can. The point is that with a scale invariant contour, you can rescale the T to pull out the factors of lambda hat. And this thing is clearly this sort of exponential thing that you're talking about. So it's gonna be a ds over s to the n e to the s, and then 1 over lambda hat to the n. I hope I got the scaling right. I wanted s to be t lambda hat.
Okay, I see. Okay, great. So yes, no, that makes more sense. Okay, cool. So now that we've laid this property out, how are we going to exploit it?
Yes. Okay. So the idea is that given a space-time field, right, we're going to be able to construct a H01, and then the consistency condition for it to be H01. So the fact that it's d-bar closed will give us a field equation on this side, just from this piece of the delta bar. So this is technology laid out by Woodhouse back in the day, before our parents were born. So okay, so let's see how this works. So I suppose I have some fields for alpha 2s. It's on space-time. I don't say anything about any equation that satisfies so far.
Right.
Yep. And then so what I'm gonna do to make it a form, a H01 that has no free indices, and has certain weights, is that I'm just gonna put a ton of lambdas, attach a ton of lambdas to it.
Okay.
Lambda alpha 2s, and now this has weight in lambda of 2s so far, and then we want it to be a form. And so let's put we want it to be a not one form in particular. So let's just take on a lambda hat d lambda hat.
Right, because this is like the holomorphic measure.
No, this is just
This is the volume.
This is just E bar not.
Oh, it's just E bar not. Okay, okay.
So currently this is omega not 1. Oops. So currently this is omega not 1.
Okay.
Yep. And then if I want to make it d bar closed, I'm gonna have to add a piece to it, because if I hit it with d bar now, d bar equals to t e bar 0 plus t alpha dot e bar alpha dot. So this piece won't do anything, because it'll wedge to 0 against this. This piece will do something, so I have to add something else to it. So let me just remove this stuff.
Right. So by t naught and t alpha dot, you mean the vector fields dual to the forms?
Oh yes, sorry. Oh yeah, I was being very sloppy. Yeah. Sorry, that's what I meant. Yes.
Yeah. So well, we will discover them momentarily, presume.
Yeah. So okay. Do I remember what this one is? Yeah, well, probably it's gonna be a lambda. Let's call it beta dot phi alpha 1 alpha 2s lambda alpha 1. So basically what I'm doing is I'm adding a piece to it that's cooked up so that it will lambda hat dx, and this has a beta dot index that's cooked up to cancel the delta bar of the first term.
Oh, I see. Right. So what you're saying is that in fact here,
Yeah.
the total D bar operator on the twister, on gamma naught one of twister space is going to have an action involving both lambda and mu, in other words, x.
Yeah.
And what we want is, basically closeness under the total thing.
Yeah, that's right. That's right.
Right. Okay, cool.
Yeah, so this is a Woodhouse representative.
I see.
Woodhouse rep. So representative because it belongs to a class of, you can add dbar of anything to it and it remains in the same class for the H01. But this is a canonical choice constructed.
Okay, okay. So could we see that, like the action? Well,
oh, okay. So yeah, of course. So so the term that will the term that we have to be concerned about if we let's call this what do you want to call it? Yeah, call it f. F equals to this plus this.
yes.
So d bar f, there'll be a term e bar 0 by alpha dot.
Yes.
And then we're gonna make sure that this term vanishes.
Yes.
But if we yeah, okay, so the contribution will be t alpha dot f0 plus t0. Oh, sorry, these are all bars, right?
Yeah, but minus a t0.
Oh yes, sorry. Thank you. Yeah, t0 f alpha dot e bar 0 e bar alpha dot. So so let's check. So what's this? This is gonna be lambda beta d beta dot what else do I want? I think that's correct. Acting on phi alpha 1 alpha 2s x and all the lambdas. Let's just all come along for the ride. And of course this term is going to be acting with lambda d by d lambda hat contracted on the second term. Oh, have I made a mistake here? Let's think about this for a second. Okay, sorry, let me just write this in.
Yeah, perhaps this has one less index.
Yeah, I think you're right.
So this is probably like something else, and curly phi, you can call it like.
Yeah, I need
curly phi tilde with one less index. Probably.
Yeah.
Or
I need
or one less lambda.
Yeah, I need a lambda hat in here somewhere. One of these needs to be a lambda hat. Oh, well, maybe I'll call this guy. This guy be a lambda hat.
Oh, okay.
And then that means that let me just count the weights to make sure that I haven't screwed something up. So this needs to be a squared. And then we'll check whether the weights of the first term and the second term are the same. Okay. So the first term has weight 2s minus 2 in lambda.
Yes.
And no weight in lambda hat.
Right.
The second term has weight still 2s.
Yes.
And minus 2. Yep. And then no weight in lambda hat. Okay. So one of these had to be a lambda hat. Sorry about that.
That's all good. Okay.
Then we can see that what happens is that this guy just reproduces this guy. This guy plugs into one of these. So I probably need a number out the front over here, one of the 2s.
Okay.
Yep.
Oh, I see. Yes. So what's happening is that we're having the field equation plus itself, or is minus itself?
Oh, minus itself.
I see.
So it vanishes, and then and then sorry, there's one more term which I neglected.
Oh, right.
sorry. Which is where the condition for the closure. Sorry.
Right,
it is important.
So this is not the field equation. This is something else.
Yeah.
Right, because you have the d beta dot by alpha instead of the contraction between the alpha and the d alpha.
Yes.
Another term.
Yes, you're right. Sorry. That was sloppy of me. So the point is that over here, right? This okay. So this term is 0, and then the second term is the the let me just okay. The second term, of course, is it's T bar alpha dot F beta dot
Yes.
skewed on the
skewed.
indices.
Yes.
So you can replace that by a contraction
With,
and
yes.
and epsilon alpha dot beta dot.
Yes.
And then so put in bottom E bar alpha dot E bar beta dot. And then you can already guess what this is going to be. So this is it's going to be the scalar field equation. Spoiler alert.
Right.
So it'll be this, right? Beta dot skewed into the
phi.
Yeah, which is this piece.
Right.
It's lambda. Okay, and I'll put the indices in now. So this needs to have a beta dot. This needs to have a alpha, and then okay, alpha 0, alpha 1, alpha 2s, alpha 1, alpha 2, alpha 2s, and then the contraction of these two, which I'm gonna write as lambda hat dx lambda hat squared. Okay, sorry. And then note that this object is actually this box.
Right.
So, yeah,
okay. So you even got the box here.
Yeah.
It's not just the self-tail parts. This is really the
Yeah. So this is it's
well. I mean, it is true that the full equation will be
Yeah.
satisfied.
Wait, okay. Okay, but where do I get the sorry, I'm probably missing something obvious here. Okay, so yeah, of course box will be satisfied.
Yeah.
But, should we what's the field equation gone?
Oh, it's subsumed presumably in the box condition.
Yeah.
Because well, you had the one condition. Well, so you had the one condition. No, never mind. I actually don't know what happened.
Yeah. What
Well,
about
that's
down
fine.
here? Yeah.
It's nice.
Yeah. Yeah, so later on we'll see that. Yeah, okay. So of course box 5 vanishing is implied by the field equation, but I can't remember what I did wrong here. Okay, wait, okay. So this part suddenly that's fine. It's canonical. You put in the
Yeah.
Yeah.
That one's somewhat
and then
controversial. I mean, if it had to come from somewhere, I'd imagine it came from this part, the first part of the
yeah,
the
it's quite possible that I messed something up here. Yeah, you're right. Because like this thing is probably supposed to be the
yeah, one of those is going to be. I'm guessing that it's happening because what happens is that you would expect that the
Oh yeah, sorry. You're right. I'm being actually, if I didn't do that dumb thing just now, right? If I just left this,
you would have been right.
I think so. Yeah. I think so, because then this thing would be killed by the lambda hat.
Yes, it would have nothing to
Yeah,
cancel
and
against,
then
and then you'd
this-
have this condition. Yeah,
Yeah.
yeah.
And then this, I can imagine that since it's symmetrized
Yes,
across
it's
these.
probably gonna
Yeah.
contract with something. Something's gonna happen.
Yeah. Sorry, let me just look it up.
No worries.
Yeah.
Yeah, let's just stop sharing.
Yeah. Oh, sorry about that. I was
That's all good.
yeah, it's been a while. I thought I knew this better.
No, this is good.
Yeah. Okay, it's called Real Methods in Twistor Theory. It's published ages ago.
Well, yeah, I mean, while you look this up, I mean, I'm confident that we will get to the resolution of this, but it does strike me that this formula has a little bit of a, I don't know, like a generating function type feel to it. That you know, like that you got this spin S field from some kind of S order expansion, like there's the S order coefficient in some presumably some expansion. And I know that there is a trick like that people use in the higher spin theories,
Right.
Right.
Yeah, I'm not familiar with this, but I have heard like Praha talk about something like this before.
Okay.
Yeah.
Okay.
Yeah.
I'm just
Yeah.
curious.
It's certainly interesting. It's all lambda hats. So this is
Oh.
the negative homogeneity case. Oh yes, I see my mistake now. I wanted to do a negative homogeneity case and I started doing the positive homogeneity case.
Right. So you
Okay,
probably want to
sorry, whoops.
swap some.
Yeah, for hats. Sorry.
That's all good.
Yeah. So okay. So I should have been doing the negative homogeneity case because it's so what you really want is all hats and then
Uh-huh.
this to the power of 2s plus 2.
Okay.
Yes. And then
There's
similarly
hats everywhere. Yeah.
all hats. And then this one would be 2s plus 1, I suppose.
Very cool.
Yeah, sounds right. Okay, and then we have with this, and then when we act with, so these are all hats. Yeah. Okay, good. And then we can try and evaluate this now. And then I've written the correct one down. So yeah, okay. Yeah. Let's count weights and make sure that I've not done anything stupid. So this has weight minus 2s minus 2 in lambda. And this has weight minus 2s in lambda. So I need more weight over here.
Okay.
Okay. Yeah, and then the weight in lambda hat is 2s plus. Oh no, sorry. This 2s plus 1. The lambda hat.
So if we just have the first term, is it evident that the action of d bar will do what we expect it to and give us the
That's a good question. Okay, so that'll be this guy here.
yes.
Yeah, it's not obvious. Like yeah, we require this to cancel against the contribution from the other term.
Right. No, but say for whatever reason I didn't have that term.
Yeah. Okay. Then the
Then
equation.
you're just compelled to have
Yeah.
such an equation, it seems.
Yeah. So you'd be saying that this
yeah, it's gonna contract
some flat directions.
Yeah, it's gonna contract the beta and the alpha ends, like well, whichever.
Right.
You're gonna get an epsilon, and then that's gonna contract the index between the partial beta dot and the phi.
Right. If we did that, that would give us the equation of motion.
Yeah, and I think that is probably what's happening in Adamo's notes, where he just writes this down, as in this first part.
Oh, okay. Sorry. Well, yeah.
So my guess is that the second part, whatever it's doing, should somehow capture like yeah, I mean maybe there's a way to also capture a second, like the quadratic, or like the quadratic and derivative part, the quadratic and momentum part. But yeah, if we were just after getting the zero rest mass equations in the first order form,
yeah,
then you probably only need the first term. That's my suspicion.
Yeah, you might be right about that. Yeah. So none of this here.
Yeah, none of that. I just drop all
the
that.
closure requirement just becomes that this must vanish.
Yeah, and that is basically the equation we had, where you have a contraction between that derivative, the space-time derivative, and
I
phi.
see. Okay, so that equation of motion would be yeah, okay, it would be this, right? Beta dot okay, so okay.
Yeah, it's beta dot alpha with alpha raised.
Okay.
Of phi alpha 1. Yeah.
Okay.
I mean, it's some multiple of this, because what's going to happen is you have this. Yeah, you have this lambda, the lambda hat.
Right.
And then
also, yeah, it will certainly contain this. I think.
Yeah.
But then there'll be the symmetric part as well, right? Which will be the so there'll be an epsilon.
It's
Yeah,
interesting.
because yeah.
Presumably, yeah. Let's see.
So presumably that's what this thing was cooked up to cancel.
Oh, I see.
Yeah.
Yeah. Well, if we went back to Adamo's notes,
Yep,
then we might see some clarification, which I guess I could share too.
Yeah.
It's fun.
Yeah. It's the interplay between the spaces. It's very
yeah, it's nice and relatively simple. Just a second. Yeah, so in his notes, what happens is that we have similar looking expressions. So the less heuristic case, yeah. So this is kind of the claim.
yeah.
Well, this is the reverse of whatever it is we're doing here.
So exactly what's going to happen is that this bit is going to tie up with all the lambdas there using this lemma.
Okay, yeah, okay. So okay, well maybe there's that's the work to do. So if you wanted to go in the other direction, then it's just like the lambda part that matters. But okay, so yeah, that's what you meant when you said that it's a Penrose transform in reverse.
Yeah, exactly. So from this using this lemma, you can just proceed to the
I see. So
this field
maybe we just dig into these old these ancient notes.
Yeah. Okay.
Not opposed to that.
Yeah.
I
can share it.
That, yeah.
Okay, so when he says right-handed fields, for us that means the negative weight one. So these are the ones that are easy to do, right? In Adamo's notes, it would be the ones where the Penrose transform procedure requires
lambdas and not
exactly. Yeah, that's the one. Yeah. Okay, there's some discussion of conform. Yeah. Well, all ZRM fields are gonna scale this way. So okay. So if you look at 5.2, right?
Yeah.
This is his potential.
Okay.
And then he defines the hat d hat, which is dz okay, dz hat, d by dz.
Okay.
Yeah. And yeah. So that's his yeah, you see, it's the negative weight. When he says z, for us, that's lambda.
Right.
Yeah.
I see. So where's the other term for him?
So this d hat operator has a d by dx as well, and it'll act on the phi, which is the function.
Right. Yeah. No, but I see what you're saying. Well, no, but his f doesn't contain a second term which had the.
No, his f is a it's not a form at all. It's a 0, it's omega 0,0. And then acting with d hat gives you the
I see. So it's like a potential.
Yeah, exactly.
So if it's like a potential, then maybe those whereas what we were dealing with is more like
it's the hat of it.
Right. So that means that we probably shouldn't be seeing well, here there's a second order equation for this thing.
Yep.
Right. Which would then in turn imply a first order equation for the curvature. And the ZRM equations in Adamo's notes are for the analog of the curvature.
Okay. Yeah.
Presumably that's the resolution to this.
Yeah, sure. But
because if we started with this being the curve, the potential, then passing d bar through it using the same logic, right, will generate it'll probably okay, so it'll generate the two terms you wanted.
Yeah.
But those two terms are not the terms corresponding to what we were calling phi before, because that was the curvature. So this is a bit of confusion.
I see what you mean. Actually, depending on what you do with the Penrose transform, you can pull out curvatures or potentials.
Yeah, I think that the basic version we're going after here just involves the curvatures.
The curvature, right. Oh, no, but I mean they originate from the same H01.
I see.
Yeah. But just depending on what else you put in the integrand. Yeah, so it's
I see. So I guess that what's going on here is that you wanted to take what was the potential,
Yeah.
right?
Yeah.
Write it in terms of the spinor indices, and then contract it with some twisters, take D of it, and then take a D bar.
Oh, wait, okay, I see what you mean, I think. Yeah. Okay. Yeah.
And then you were right. Whatever you're doing was completely right, because
Yeah.
what you're going to be getting is, I mean, if you had the contraction, the thing that I was mentioning before, I mean, I
Yeah.
misled you.
No.
I think you're on the right track, because if you have that contraction, that's like a gauge condition. That's not an equation of motion. In terms of the potential, you have this quadratic equation of motion, even if it's just purely self-dual or purely anti-self-dual,
Right.
and that's going to involve the box.
Oh, I
So
see. I
yeah,
see, I see.
you were right all along. We could just go back to your notes then.
Uh, I also screwed up the
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 hats
hats
with
at
the
the start
unhats.
because I started writing down the positive homogeneity thing instead of the.
But the rest of the logic probably carries through,
Yeah.
because so what happens is that you do probably get this cancellation between the first couple of terms, and
Yeah.
then the second calculation involving the purely horizontal directions
Yeah.
will give rise to now a second order field equation.
Yeah. I see.
But that's not, I mean, that's still equivalent to the first order equations I wrote down at the very beginning. It's just that phi is not the same phi.
Okay.
Right?
Yeah. Yeah. I think that's right. Yeah.
Yeah. So okay, that's great. So this is okay. So this is the content of the Woodhouse
Yeah.
representative. And just to recap, like what we had in the notes by Adamo, the opposite is what happens with the Penrose transform,
Yeah.
right?
That's right.
That you take
The restriction of this guy onto the fiber direction.
yes.
So you just take this component, and then you I can copy that and write it on the
Sure.
somewhere else. We use we wedge it into this F, right?
Yeah.
Take lambda d lambda, and then enough powers of lambda, sorry, beta, I suppose. Beta. On the support of the incidence relations, and this just spits out your with the lemma that we used earlier. This is restricted to the line u1x.
Yes. Yeah, and that's using, okay. No, so that, yeah, this does seem a lot like this F is kind of generating function for this phi. But yeah, I think that's just something to go track down in the higher spin literature. It was inspired by the same thing. So that's very cool. So I think I at least understand better the origin of the Penrose transform.
Yeah, it's very interesting.
Yeah. And well, I guess we should just at least mention in words the things people can now do beyond this first result, right? So this is something figured out many years ago.
Yes.
Applied to spin, I guess, spin 1 and spin 2, and sort of thought about it a little bit harder, you get the Ward correspondence and the nonlinear graviton construction.
Yeah.
And then there's now sort of quantizations of these, right? So there's like some very interesting literature about that. And these are some of our friends and colleagues whom I can ideally pull onto this podcast sometime.
Yeah. Like David will have a lot of interesting things to say about this at the level of actions.
Love to talk to him.
Yeah.
Yeah, I mean, no, that is very interesting. But just going back to some geometrical points. So in some sense, the natural thing to think about constructing twistor space as a bundle over rather than R4 seems to be S4.
Yeah, definitely. That's certainly true. Yes. The
Right?
origin CP3 is bundle of S4.
And if you now if you just complexify everything, you could kind of sleepwalk your way into ADS4 also.
Yes,
if
definitely.
you
Yes,
wanted to.
yes. Yeah.
Or DS4 for that matter.
Yes. Any slice you like, any real slice you like out of C4, complexify S4. Yeah.
Right. And is that the kind of thing that you're doing with ADS5 now?
Yeah, pretty much. So okay, so yeah, yeah. So in the paper that we're writing, there's little to no consideration for the particular real slice that we're working on, right? We simply it's just complexified space-time, one of these spheres, pseudospheres.
Uh-huh.
Yeah, and there's not really any consideration. We're just being a bit lax about it. Yeah, but it's certainly true that you just based on a real slice, you can just get S4 or ADS or DS.
Right. And then there's still a notion of infinity that you can make sense of in all these contexts, right? So is it like in flat space that you have a neat way to think about the asymptotic boundary as where the conformal factor blows up?
Okay, so that's it's a bit more difficult. So okay, so the 4D case, right? When we're thinking about S4, DS4, ADS4, there's more small literature about this. The odd dimensional case that we were trying to do is a reduction of our C6. The writing ADS5 is a reduction of C6 is a bit unclear what the boundary corresponds to in terms of twistor space boundary. But okay, but for 4D, so you pick something known as an infinity twister,
Right?
Yeah, and that tells you something about the conformal boundary. I don't remember the details of this, but I know it's in the notes.
Yes, indeed it is. We covered it last time to some extent.
Oh yeah, excellent.
But it is, I mean, it is a very interesting tool to say that, well, if you want it to be, if you just complexify everything,
it looks like
then you can really forget whether you were on the asymptotic boundary of ADS, the future asymptotic boundary of DS.
That's true. It's not clear what's time like space like.
It is
just work to see.
Yeah, no, it would be very interesting to see if there's any holographic use to this to this observation.
Yes, I see. Like importing results from
Yeah, I know that in the higher spin world, the higher spin holography world, there's a lot of use for this.
Oh, right. Okay.
Yeah, well, basically the idea is you exploit the fact that you can make sense of interacting higher spins on ADS or DS.
Yes.
And then to talk about the conformal boundary, you use these structures in twistor space.
Oh, right.
That's kind of the idea, I think, roughly.
Yeah.
Sorry to all my friends who work on this that might be getting this a little bit wrong, but yeah, that's kind of the idea. But now that there are all these other twister actions, like for the kinds of theories, relatively more local theories that people can now put on twistor space, it's just a very interesting question as to whether you can import these twistoral techniques from the higher spin world.
Yeah, definitely.
Yeah. No, so there's much to learn, and you've been very generous with your time, Sean. Thank you so much.
Yeah, thanks for having me.
Yeah. So this is Directly Podcasting. If you've come this far, like, share, and comment, and subscribe. And I will catch you later.